Hello, welcome to Chapter 10.1 from Stevens' Introduction to Statistics, the Think and Do book. In this chapter we're going to talk about correlation. And way back in Chapter 3 we looked at scatter plots. And back then we said we can use these scatter plots to help determine whether or not there's an association or correlation between two variables. So we're gonna dive a little deeper into that, clarify the difference between correlation, association, and when there is a significant correlation and when the correlation is not significant. Okay, so we look at the first couple scatter plots here. We have cricket chirps versus temperature. Down here is the temperature. Here are the cricket chirps per minute, right? And what you should notice is as the temperature increases, the rate of cricket chirps gets higher, right? We can spot that pretty easily from this scatter plot. And the other thing to note is that both of these axes have quantitative variables, right? So that's necessary for a scatter plot and for a correlation. And you know, each one of these dots is actually a point, which consists of two numbers: an actual temperature, which looks like it's maybe 92, and then a rate of cricket chirps, which looks like it might be, say, 220. Right? So each one of these dots on the scatter plot is actually a point consisting of an x value and a y value. All right. And over on this other graph over here, we look at some demand data, and what we see down on the x-axis is the price for an item, whatever it is, widgets, and on the y-axis it's the number sold. All right. And what you can see from this graph is that as the price gets higher, right, the actual number sold goes down, right? As the cost increases, the number that are bought goes down. So this is going in that direction, whereas the cricket chirps are going up. Okay, so let's define some terminology. A strong relationship results in a scatter plot that tightly follows a line or curve, right? That's a line or curve that we almost have to imagine at first, right? You sort of look at it, and can you see a clear pattern, right? A positive relationship results in a scatter plot that goes up from left to right. So this cricket chirps versus temperature is a positive relationship. A negative relationship is one that goes down from left to right. So this demand data has a negative relationship between price and demand. And two variables are linearly related if the scatter plot reveals a pattern that follows a straight line. So if it's clearly following a straight line, then we say the variables are linearly related. Right? And these, you know, both of these, you can sort of see a line with the cricket chirps, and you can sort of see a line. You know, it doesn't have to be a perfect line, but it just has to be a pretty clear line that it is following with some variation around it. An association exists between two variables when they are related in some way, and a correlation specifically means that there is a linear relationship. Right? So correlation implies linearity, right? Association is in particular vague, right? It could be linear, it could be a curve, it could be U-shaped, it could be, you know, up and down. So correlation specifically refers to the linear relationship, whereas an association can be any relationship. All right, so your turn. This stuff in red is not in your book. Describe each relationship as weak, strong, positive, negative, linear, nonlinear, association, correlation. So when I look at this one, the first one, it looks pretty strong, right? And most people agree that that's strong. It's following a pattern pretty tightly. It is certainly negative because it's going down from left to right. It's linear. I mean, you can draw a line through there, and it matches it pretty well. And so that immediately implies correlation. So we would call that a strong negative linear correlation. Let's look at this one, the second one. It looks pretty strong because it looks like, I can plot a curve that goes through that data pretty well, right? So it looks like it's following a pattern pretty tightly, so we'll call it strong. It's certainly positive as it's going up from left to right. This part is kind of flat, so it might not be anything there, but certainly on the right portion, it is a positive relationship. It certainly looks to be nonlinear, right? Because you can't draw one line that fits this stuff, right? You might be able to draw two lines, maybe a flat one here, and then another one there, and then another one there, but that's not a linear relationship. You have to be able to draw a single line. So it's nonlinear because it looks like it's following a curve. And so that makes it an association, right? We don't call it a correlation if the relationship is nonlinear. And then we look at this third one, and this is hard to decide whether it's strong or weak, fairly strong. And we'll get into defining strong or not strong, and we won't use the term strong, we'll use the term significant. But if you look at this, I think, in my humble opinion, it's fairly strong. The relationship, I put a line through there, it's kind of matching it, so fairly strong with a question mark. Negative, because it's definitely going down from left to right. I'd say linear, because you don't want it. The goal is not to connect these dots with this type of line. Or this type of curve. You're not looking to connect the dots. That's clearly not linear. But we're looking for more of a general linearity with some variation around it. So I would call that fairly linear, and because of that, we call it correlation, right? Then this fourth one is definitely a little harder to call. It certainly seems weak. Positive or negative, it's hard for me. That's why the question mark. If you're over here, it looks negative. If you're over here, it looks positive. But then if you try to draw a line through the whole thing, I would probably think that it's positive. That's why I have positive, but there's a question mark there. Because, first off, it might not even be linear. If I had to draw a single line through there, that's a terrible fit. But it might be U-shaped. There might be some sort of underlying U-shaped relationship. All right. So is it linear? Hard to say. So therefore, we would just use the word association. If we don't know that there's actually a linear relationship, the variables are related by an association. We just use that word by default. Okay, so there we go. That's sort of the game we play. And we're going to get into, how do we quantify the strength of a linear relationship? And we do that with the linear correlation coefficient. Right? That's going to tell us how strong a relationship is. It's given the letter R. Formally, it is called Pearson's correlation coefficient. And it has the following properties. R is between -1 and 1. All right? The closer R is to 1, the stronger the positive linear relationship. Take a look down here at this graph. R equals 1. That's a perfect linear relationship. The closer R is to -1, the stronger the negative linear relationship. So that's this second graph. So there's a perfect negative relationship. And this 1 and -1, it doesn't refer to the actual slope. It just tells us if it's +1 that it is increasing, and if it's -1, it's decreasing. Right? That isn't the slope. A lot of people think that might be the slope, but that isn't the slope. But it does capture the sign of the slope. R measures the strength, how tightly the data follow a line. And the closer R is to 0 here, the weaker the linear relationship. So here is a scatter plot which has a correlation coefficient of 0. And it's actually kind of hard to randomly generate data that gives you a 0 correlation. But that's what it looks like. It looks like sort of a shotgun blast right into the chart. Okay. A couple of properties. The value of R does not change when the variables are converted to a different scale. For example, when we had cricket chirps and temperature, that was in chirps per minute and temperature in Fahrenheit. If I had switched that to, say, chirps per second and temperature in degrees Celsius, the correlation coefficient would not change. And the value of R is not affected by the choice of X and Y. In other words, if I switched cricket chirps and temperature, if I put the other one on the x-axis, switch that original x-axis to the y, the actual correlation coefficient would not change. So here's let's just get a look at what some of these R values look like. So we looked at R equals +1. That's a perfect straight line. R equals -1. Perfect decreasing line. R equals 0, sort of a shotgun blast. Here's an R equals 0.834. So you can still sort of see it pretty clearly what's going on. R is -0.7, so it's still a pretty strong linear relationship. R equals 0.229. At this point, you'd be hard-pressed to freehand a line that goes through there, right? Same thing with -0.19. All right, so as it starts getting down around these numbers, it gets harder and harder to spot any sort of relationship. And then finally, over here, R equals 0.077. So that's a very weak linear relationship, 0.077. So there's almost no correlation. But notice there is a very strong association, right? So the correlation coefficient only captures the degree to which the data follows a straight line. You can have a really nice pattern here, like we do in this problem, and it is not captured by the correlation coefficient. All right, how is the correlation coefficient calculated? It's calculated with this formula here, where it's the sum of all of the x values minus their mean over the standard deviation of the x values. And so if you look at these, this whole thing, those are all the z-scores for every x value. Likewise, these are all the z-scores for every y value. And you multiply those together, add them all up, and you get the value of R. You should avoid doing this by hand. In this chapter, I'll give you the correlation coefficient. But all statistical software packages and graphing calculators have functions for creating scatter plots and calculating R. And you can find some examples at stevenstats.com. So I'll give you R, or you should use software. This formula is just too hard to do by hand. All right, so now we're going to get into, when is a correlation significant? Because we were talking about, a strong linear relationship or a weak linear relationship. We're going to replace that with significant or not significant, right? So when is a correlation significant? And we have another table for that. It's table 4. It's on page 292. All right? And here's the way you use that table. So let's go over there. Here it is, page 292. So this is table 4. The critical values of the Pearson correlation coefficient are. So here's the idea. If you have a value of R, your correlation is, say, 0.718, then you look, and you have to have your sample size is, say, 10. What we do is we look down here at 10, and the critical value is 0.632. So if this is your case, then you have a significant correlation, right? Because you have to beat this value in R for your given sample size, right? For example, if you had an R value of, say, -0.612 and your sample size was 14, you'd go down to the table here. 14, I have to beat 0.532. I have a -0.612. So I want to draw your attention to something. You have to look at the absolute value of R. If your absolute value of R is greater than the one in the table, then we conclude that there is a significant linear correlation. So in this case, the absolute value of R is 0.612, and that is in fact greater than 0.532, the critical value down here. So this is a significant linear correlation. If you had a sample of size 14 and a correlation coefficient of negative 0.612. Right, so you have to beat the value in the table. If your n, here's the sample size. If your sample size is not listed, use the nearest lower n. Right, so you use the smaller n, just like with the degrees of freedom. Okay, so let's clean this page up a little bit and go back to our problem. Okay. Significant or not? And by the way, if you're using software, it doesn't really give you a critical value to compare your correlation coefficient to, but it will give you a correlation coefficient, and then it will give you a p-value for the correlation coefficient. And generally a p-value of less than 0.05 is considered significant. And it depends. There's actually a hypothesis test going on in the background. But this 0.05, those critical values that are in the back of the book, those are based on a 0.05 significance level. So if you use software, it will probably return a p-value, and if the p-value is less than 0.05, for the purposes of this chapter, we'll call that significant. Okay. But you can always just use the table. Alright, so some examples. Use table 4 to determine if the given correlation is significant. When correlating car weight and fuel economy, the correlation coefficient from a sample of 7 cars was negative 0.944. Right? So we go to table 4, we look for n equals 7. Right? So when we go to n equals 7, our critical value is 0.754, right? 0.754. We bring that back. 0.754. And the thing to notice is that the absolute value of your correlation, of the correlation coefficient for the car weight and fuel economy, is 0.944. That's bigger than 0.754, so that we conclude the correlation is significant. The your turn problem. When correlating mother's heights and daughter's heights, the correlation coefficient from a sample of 8 pairs resulted in a correlation coefficient of 0.693. Is that a significant correlation? So I have n equals 8 and r equals 0.693. So let's see. N equals 8. N equals 8. 0.707. So the critical value is 0.707. We need to beat 0.707. Right? So our value of r is smaller than the value of r in the back of the table. So this correlation is not significant. Right? Suppose, and then there's a little second part here that's hiding at the end. What if there had been 20 pairs in the sample, right? If n equals 20, what does that get us? You should notice that as the sample size gets bigger, the critical value gets smaller. So if there was 20 with that same exact correlation coefficient, that would suddenly be significant, right? So you need you don't need as high of a correlation coefficient when your sample size gets bigger. So 0.444 is the critical value when n equals 20. So what that means is if n equals 20, we actually did have a significant correlation. Right. So whether or not the correlation is significant does not only depend on the value of the correlation coefficient, but the sample size as well. All right. Let's talk about a few things that can mess up our little system for correlations. We're going to talk about outliers here. All right. And they can make or break a correlation. All right. If they are known to be in error, they should be eliminated. If not, then you should probably investigate the situation further. So here in this case, we have an outlier that makes a correlation. So what I did, I had 15 students in a classroom, and they all took an exam, and I wanted to see if there was any correlation between the time needed to finish the exam and the score. You know, because some people think, oh, you get done earlier, you did better, or some people think, oh, you got done earlier, you did worse. I wanted to see if there was a relationship. And so here is the scatter plot for the entire class. It gives the time it took each person to complete the test and their score on the exam. And what you'll notice is somebody only took 10 minutes and they got like a 17. So this is like 10 and a 17. So they didn't do so well, and they didn't put too much effort into it. So that's basically an outlier to the rest of the class, which is over here. The problem is when you calculate the correlation coefficient for all 15, right? You get a correlation coefficient of 0.694. And if you look for n equals 15, I need to beat 0.514. So my correlation coefficient results in a significant correlation. So there's a significant correlation with this data. All right, it's positive, which goes like that. So you might start thinking, oh, the longer it takes to complete the exam, the better you do. But in general, that's not true. The only reason we have that significance is because of this thing. If you look at the rest of the class, draw a little box, you can pretty much guess that that is not going to result in a significant linear correlation, right? It's the outlier here that made that correlation. So that was a sort of a fake correlation, right? Even though it came up as significant, it was due entirely to this one outlier. So that's where an outlier makes a correlation. An outlier can also break a correlation, right? For example, if you look at this data, and there's no axis label, so we don't know what it is, but what we can see is that we've got a really nice correlation here, except for this outlier, right? And if you find the correlation coefficient for everything, you get R equals 0.545 for n equals 12. And if you look for the critical value in table 4, for n equals 12, we need to beat 0.576. So we don't actually beat. 0.545 is less than 0.576. So in this example, this scatter plot reveals a correlation that is not significant. But that's because this outlier wrecked it, right? It's a correlation wrecking outlier. Because if you got rid of it, if this thing was gone, you can see, you don't always need to calculate the correlation coefficient to say, yes, that is a good linear correlation, right? So that good linear correlation, which was most likely significant, has been wrecked by that outlier. So outliers can make or break a correlation. Interpreting R, this is used regularly and usually used incorrectly, but we'll use it because it is just so tempting, and it allows us to take the value of R and impose some sort of explanation of what it means, right? So here's what you do. It's called explained variation. If you take R and square it, then what you get is the explained variation. But you have to remember to square it. And that value of R squared represents, and this is a strict mathematical statement, the proportion of variation in Y that is explained by the linear relationship between X and Y. Right? For example, if you come over here, where we have cricket chirps and temperature, right? A positive linear correlation. So if you look at this, The correlation coefficient is 0.936. And if you take 0.936 and square it, you get 0.876. So what that means is about 87.6% of the variation in rate of cricket chirps can be explained by the linear relationship between cricket chirps and temperature. Right? So what does that mean? Does that mean that the temperature caused the cricket chirps to change? It certainly stands to reason that that is the case, but that's not really what we're saying. We're not really saying 87.6% of the change in cricket chirps is caused by the change in temperature. We're just saying that the proportion of variation in one can be explained by the linear relationship that exists between the two variables. So it's a strict mathematical statement, but it's often used to imply cause and effect. And if it's not used to imply cause and effect, plenty of people infer cause and effect just purely from the way it is stated. For example, you can actually switch the implication here, and you can say that a perfectly valid mathematical statement, about 87.6% of the variation in temperature can be explained by the linear relationship to the rate of cricket chirps. So it sounds like I'm saying that the change in temperature is caused by a change in cricket chirps, but that's not quite what I'm saying. I'm saying that the variation in one can be explained by the linear relationship between the two variables. So cause and effect is often implied or inferred, but it's not meant to. It's actually a strict mathematical statement. But it's just so tempting. So it gets used a lot, and I will occasionally do it myself. Okay, your turn. When correlating car weight and fuel economy, the correlation coefficient from a sample of 7 cars was negative 0.944. Estimate the proportion of a car's fuel economy that can be attributed to the linear relationship to a car's weight. Nice and simple. Take negative 0.944, that's R, right? You square it, you get 0.8911. So about 89% of a car's fuel economy, about 89% of the variation in a car's fuel economy can be explained by the linear relationship between weight and fuel economy. And there's, I didn't really put a cause and effect in there, but it certainly seems to make sense. What makes a car fuel efficient? It's weight. What's the biggest player in how efficient a car is? It's weight. How much of a role does that play? About 89%. So it does give us something to grab onto. Though it's a strict mathematical statement, it certainly helps quantify the magnitude of a relationship. Okay. In a sample of 11 U.S. cities, the correlation coefficient between population and murder rate was 0.727. Make a statement about the dependence of the murder rate on population. So if I take my R and I square it, I get 0.52852. So if I convert that to a percentage and with no decimal places, I have about 53%. So the correct way to say this is about 53% of the variation in a city's murder rate can be explained by the linear relationship to population. It doesn't mean that the population causes the murder rate to increase, but it certainly suggests that, doesn't it? So the cause and effect which is implied or inferred may in fact exist, but we're not quite saying that it does. All right. Okay, issues with correlation, causation. So we're getting in a little more into this causation problem. Correlation, causation, and lurking variables. Don't say correlation when you mean association. This word association is deliberately vague. Correlation deals specifically with a linear relationship. Correlation versus causation. Popular confusion. Scatter plots and correlations never prove causation by themselves. While the relationships are often indeed causal, meaning one does cause and the other one to change, the nature and direction of this cause and effect is maybe hard to establish. you always want to be on the lookout for lurking variables. A lurking variable is one that is not, in the scatter plot. So you have a scatter plot, one variable here, one variable here. There could be some third variable, z, that is causing the two to go in tandem, right? So it might not be that x is causing y to change or y is causing x to change. There could be some other variable, a lurking variable, causing them both to change together. But then on the other hand, so the correlation doesn't prove causation, right? But on the other hand, it does provide evidence that there is some type of causation relationship happening somewhere. And it's certainly worth investigating. The cause and effect, it might not be the one you initially expect, and it might not even exist, but there is, good reason to believe that there is something going on there. All right? So the problem with this statement, correlation doesn't prove causation, is some people will take a correlation that they don't like and just throw it out and claim correlation doesn't prove causation. On the other hand, correlation doesn't mean there isn't causation, right? So you don't want to just throw out the causation possibility because of this statement, right? It's always worth looking into the cause and effect relationship because that's really what we want to learn, right? So chapter 10.4 tells us a little bit more about how we do that with multiple linear regression. Okay, here's some examples. Despite this very strong correlation between smoking and lung cancer, it was known for about 100 years. But it took about 100 years to prove that smoking was causing the lung cancer. Because they really had to prove it in a court of law. So the proof had to be, closed. It had to be a closed case. They really had to prove it. And it took about 100 years to develop the methodology to make that case. And the tobacco industry had this counsel that defended them for years and years, and basically they kept saying, correlation does not prove causation, and they were able to basically use that argument for decades. And then eventually in the controlled studies and gene studies from the 1980s and 1990s, they did have an airtight case, and they did prove cause and effect in one direction. But it took a long time, and that's because the tobacco company's defense kept going back and quoting, correlation doesn't prove causation. And so it took 100 years for people to finally officially recognize that. Which brings us to a similar situation, global warming. All right, in the scientific community, there's a strong consensus that global temperatures are rising, and this rise is primarily caused by the increase in greenhouse gases produced by humans. All right. However, the dispute about cause and effect still exists in popular media. On TV, you hear a lot of, in the media, they're like, well, no one's really proved that. And if we've learned anything from the smoking situation, it can take a long, long time to prove something. And the difference between our smoking and cancer and our global warming situation is that at least with the smoking and the cancer, there were thousands of cases to check and do controlled studies and experiments. Whereas with the global warming, of course, there's only one Earth, and so we don't have that data. We don't have a whole bunch of Earths to see what happens when humans do different things. All right. So waiting for absolute airtight proof that human endeavors are causing the rise in temperatures could take another 100 years, which is far more time than we have. All right, so here's some less heady examples. Books and grades. There's a strong correlation between the number of books in a child's home and his or her performance in elementary school. Does this mean putting books in your house will cause your child to do better at school? What are the lurking variables? Well, of course, you can't just throw a bunch of books in the home and then wait for the student to do better in school. The lurking variable is probably the home atmosphere, the appreciation of reading in the household in general, or the appreciation of education in general, right? So it's not the books. The books themselves can't cause us, a child to do better in school. They might help. There's a significant correlation between the price of rum and the salary of statistics professors. I like this one because students come up with some of the most wonderful reasons why the salaries of statistics professors could cause the price of rum to increase. They're not all very flattering. But basically, if you look at, say, the price of rum and the salaries of statistics professor, as time proceeds, both of these will go up, right? Inflation, because we have no time. This is maybe 1982, 83, 84, 85, maybe it went down 86, 87. So what's going to happen with time is that we're going to get points up here. They're going to start creeping up that way, and it will give the look of a positive correlation. Actually, there will be. You can almost get a positive correlation between the price of any two things. What you want to do is constrain it to within a specific time period so that inflation is adjusted for. So it's inflation. Not that we're not driving, us statistics professors are not driving the price of rum. We're not spending all of our extra money on rum. Okay, there's a strong correlation between ice cream sales and death by drowning. Does ice cream cause drownings? Of course not. The lurking variable is temperature or season. It gets hot, or you're in the summer. In the summer, you eat more ice cream. There's ice cream trucks. There's also more swimming, and there's going to be more drowning. So the lurking variable is the temperature or the season. There's a significant correlation between the rate of cricket chirps and temperature. Does this prove that increased temperature causes crickets to chirp faster? Is it possible that the faster chirping causes the temperature to increase? Could there be a lurking variable? If you want to extend your imagination, you could say, well, maybe the cricket chirping, they're rubbing their legs together, causes friction, causes heat. Maybe that's causing the temperature to rise, but we all recognize that as crazy talk. Maybe there's something about the mating season. As the summer proceeds, maybe they get a little more desperate for a mate. They rub their legs together faster, and that just so happens to correlate with temperatures getting warmer. But more than likely, and you don't want to throw out reasoning, right? More than likely, warmer temperatures loosen up those tiny little cricket legs, and they're able to chirp faster. But I guess I could be wrong. Who knows? There's a positive correlation between the amount of rat poison in a house and the number of rats in the area. Does more rat poison increase rat populations? Of course not. It goes the other way around, right? One is causing the other one to appear, but it's the rats that are causing the rat poison to appear, not the other way around. The causal relationship probably goes in the other direction. All right, so we are done with Chapter 10.1, correlation, and in the next section, we'll actually look at taking our scatter plot and our correlation and finding the line that best fits the scatter plot. But that is 10.2, so we are done here. I will see you then.